Okay, welcome to the 8th practicals of ESP. Today it's the second last time. Next time we will have some special lecture, and I think David and Sebastian will tell you a bit more about that. But today our practicals are very packed. We have a lot of things to do. So let's start immediately. As always, a bit about organizational matters, and then we will have a recap on everything we did last time. So the whole dynamic memory again, because this is really important in this course. And then we will extend these topics with the dynamic user input. You need something similar for assignment 3. And then we talk about data structures, in particular the 2D array on the heap. So we saw it on the stack at some point, 3 weeks ago, I think. And now we discussed it on the heap, and we will also talk about linked lists. Okay, but the organizational stuff first, so the boring things.
Okay, this is just mostly the same as last time. Just one important thing, we extended the time frame for coding session 3 and homework 3 by 1 week. So you have 1 more week to register for coding sessions and to complete your homework. Okay, for assignment 2, we now finally pushed your grading, so we corrected everything. As always, you can view them on our grading page. It is linked in the announcement on Discord, and yeah. And maybe important, if you have any questions about your grading, if it's not super important, then wait for the assignment interview. There your tutor will talk about A2 and A3, about your grading and the stuff you did. Maybe have a look at the comments in the grading, because if you did any mistakes that cost you points in A2, it would be very nice if you figure them out now by looking in your grading, and so that you don't repeat them for A3.
Yeah, A3 is already the correct word. Yeah, deadline is next week on Wednesday. We have a question hour for assignment 3. It's on next Monday at 6 p.m. and it's in the lecture hall, HSI 3. This is Infeldgasse 25D, I think. Yeah, it's linked in the announcement that we will write after today's practicals. The most important thing about assignment 3 again is that you really take dynamic memory serious, and that you follow our guides that we presented last time here on dynamic memory. We will also recap this today, but this is the most important thing on A3. Yeah, and regarding assignment interviews of A2 and A3, they will be starting from the 13th of December and mainly in the week then from 16th of December to 20th of December. We try to fix all the time slots by Monday, that you can already register approximately 1 week in advance. The most important change to the assignment interview of assignment 1 is that you will need to code during the assignment interview. So you will receive a short task, and that you need to code live during the assignment interview. And we cannot predict how long you will need for this task. This could be 10 minutes if you are already a very good programmer. It could be 20 minutes, 30 minutes. It could be also an hour if you are not that sure at the moment. Maybe have included some bug during programming there and need to figure out what is the problem. And hence you should plan for the assignment interview for at least 1.5 hours. Because we don't want you to fail the assignment interview only because you have to go and are not able to finish your code. Usually it would take, 30 minutes, I think, to complete the task. But if it takes longer, please, book a time slot then, where you have some time afterwards as well. But we will announce this on Monday on Discord, and then you can read through it again and register. Okay, first topic of today, the recap of dynamic memory.
So I won't be doing the whole recap about what every function does. I think we'll see a bit about this later by you, but I will discuss something that you need for A3.
Yeah, but first we have to recap.
First we have to recap. Okay, then we do dynamic memory.
But we need everything for your task then, because you will need all these functions there. Let me just do the recap first. So malloc was the fundamental function there, which allocated us memory on the heap. And remember this, the most important thing here was, if you use malloc, you need to implement the null check after the malloc. And if malloc returns null, so there was no space available anymore, then you need to free all previously allocated resources. So if you have 10 mallocs and the 10th malloc fails, you have to free the memory that was allocated in the first 9 mallocs, and then you need to terminate the program. So malloc is rather simple. Then we have the checklist for realloc. If you use realloc, you need to assign the return value to a temporary variable. You need to check the temporary variable to be null or not. And if it is null, then there was a problem when reallocating. And again, you have to free all previously allocated memory. And this also includes the array before the reallocation operation. Because the array exists, then you do the realloc fails, but the array before the realloc still exists, and you need to free it as well. And then you terminate the program. If you have this temporary variable and everything went fine, then you can assign it to the pointer back and set the temporary variable to null.
Yeah, it's really important that you take care when you do realloc, because this is most of the time when stuff goes wrong.
We can also view it in the code from last time. Maybe start from here, from the malloc operation. You take the return value of malloc, you need to check it for null, and if it is null, you need to free everything. Okay, nothing was allocated before, so we don't need to free anything here. Print an error message. It is described in assignment 3 how this should be done, and then you terminate the program. And the realloc, we said it's really crucial that you use a temporary variable for the return value of realloc. Then you... Sorry? Yeah, of course. Better? One more, then... that's probably too much. Maybe, I don't know, maybe. No, I cannot zoom like with intermediate values. Okay, so the realloc, you need to take the temporary variable, assign the return value of the realloc to the temporary variable, because if the realloc fails, you need to have access to the array from before. And if you assign it here to my array directly, then you lost the pointer to the previous array. So you need the temporary variable, you can free the array, print the error message, and return and terminate your program. If everything is well, then you can overwrite the pointer from before with the temporary variable. This is important. You really need to do it exactly this way. Otherwise, if this free is missing or if the temporary variable is missing, you will receive point deductions in A3 and A4, but mainly now in A3. Have I missed something on the realloc?
Yeah, I think it's just important that you free all the memory and not just, like in our example, we have one free, but there could be multiple frees. So
yeah, so if we have like 5 mallocs here, and then a realloc is not working, then we have to free all the 5 mallocs from before. So wherever you terminate your program, everything must be freed before. Okay, and the free operation is now rather easy. Just remember, free everything in every possibility how your program can end. If it's end because user input is incorrect, the user, I don't know, enters done or quit or something, or the memory, you run out of memory. In all these cases, you need to free everything before you terminate the program. And this is just a hint. It's not completely necessary, but it's helpful. If you free a pointer or do not use a pointer anymore, then please set it to null, that you cannot work with the invalid memory by accident later on. This is really important. We did this all last time, so if you're not familiar with this, I would really encourage you to watch the last practicals again. Yeah, but we will also do an example on this now today, and I think now it's your.
Maybe let's try something. Oh, like this.
You want to set the zoom?
Is it more readable like this?
It's just the font size the problem, but I think we can.
I don't know. I'm not sure.
Yeah, make it one larger, but maybe go back to the black mode, I think.
I thought maybe we have more contrast on the projector this way. Okay, then let's continue with dynamic user input. So you will need this for free. Of course, the last few you also need for free, but you also need this because we need arbitrary length input. So the user can input as many characters as they want, and our program should be able to handle it in a meaningful way. So we also want to store them and not just discard them like we did in the last assignment. So it's really we want to store an arbitrary input. Okay. But how could we do this? Well, if you think back about fgetS, how did it behave? Well, with getchar and scanf, I think we did 2 examples where we showed how the input buffer behaves. So if you don't read a character, then it's left in the input buffer for you to read later. And these unread characters could be read later. So does fgetS do the same thing? I think we should try this out. Do you have a file for me?
Yeah, you can use the main.c.
Okay.
We don't need this anymore.
Okay, so the thing I want to do is now just see how, if this fgetS, if it leaves some characters in the input buffer, if this behaves the same way you would expect with getchar. So let's just create 2 buffers. A buffer 1 with 5 characters, so I don't need to type that much. We have 5 characters. So this 5 is with the \0, so with the 0 byte, null byte at the end of our string. So actually we just can save 4 characters. And yeah, here the same thing. And what I want to do now is enter in the first fgetS, I want to enter more than 5 characters and see what this fgetS does.
Maybe a \n that we can see it better.
Maybe do also something like this, so we see white spaces more clearly. Oops. Okay, let's try this out. If we enter something, for example, 1, 2, 3, which fits into this buffer, because now I will also enter the new line, which will be saved, and the \0, so I can basically only enter 3 characters here. Then, as we expect, the second fgetS prompts us for new input, which I can do, and now I can also type in more, then fits into the buffer, and we can see that the first fgetS just read as much as fit read everything here, and the second FKS just stopped. And if we enter more than fits into the first FKS, then we can see, okay, we are not asked to enter anything for a second time because the input buffer still contains some characters. Because we are reading this 1, 2, 3, 4, then the 0 byte fits into the first buffer, and then the second FKS reads this 5, 6, and the new line I typed here at the end. And then the 0 byte. Okay, so what did we observe? Well, FKS really leaves like the getcher, the unread byte in the input buffer as we expected. And with this behavior, and with now knowing what realloc does, we could come up with something how we read this arbitrary length input. So let's use this. Well, first we just alloc a buffer with malloc and choose some initial buffer size. Then read as many characters as will fit into this buffer. And then we need to somehow check if we're not at the end of the input. And if we're not at the end, we want to increase the buffer size and then repeat. So again, with FKS, read the next characters as much as fits into this new resized buffer. And if we are at the end, then we can stop and we don't need to resize the buffer anymore. And using this, as we can see, if we do all of this correctly, then we call FKS multiple times, but still we only enter something once, because if we're at the end of the input buffer, so if not at end here, then we don't call FKS anymore and the user is just prompted once. And this is what we want. If this was a bit abstract, I'll do an example now, and I also have visualizations so that everything could hopefully becomes clear. So I'll use constants, so I'll just, declare some buffer size, and I want, just for demonstration purposes, I will make the buffer 5 characters big and then always increase it by 5 characters.
Maybe at this point, a hint for assignment 3. If this input doesn't work for you and you simply try to increase the initial buffer size as large, such that every input of our test cases is smaller, then this is not enough. Really, what Julia shows you now, this must work with the realloc, and it should not only work by chance because you choose an initial buffer size of 1 million, such that every input can be stored in it. It really needs to execute this realloc, and we will check this also by hand.
Yes. So we really want to write something that theoretically could handle an input as long as we want. And if we just make a buffer of size, 1 million, then most of the input would work, but not all input, because I could enter an input with 1,000,001 characters. And I want to really store everything. So let's just start. I'll create a buffer with malloc now, because I want to increase it at a later point. I'll write this size of char here, because we want to store characters. Size of char is of course just 1, but just so, so you don't forget it when you do not use characters. And then, as we've learned, with malloc, we always need null checks. So if this buffer is null, we need to free all memory we allocated before, which is none, so we'll just return. Okay, so now we have a buffer, and I want to read into this buffer. We know we have made it this buffer size, and then read from std in. Okay, then at the end, we'll probably print it. I mean, we can try this. If we enter something that's too big, for example, here we won't get the new line. And if we enter something that does fit, then yeah, we'll have everything I entered. Okay, but let's get to the interesting part. If we go back to the slides. No, I had it here. Yeah. We now read as many characters as fit into this allocated buffer. I now want to check if we're not at the end of the input. I'll leave this as a to-do. How could we check if we're not at the end of the input? Does anyone have an idea? Yes, so \n. If the buffer contains the \n, then we know that the user hit return and this is the end of our input. Or maybe doesn't contain because we want to check if we're not at the end.
So you assume now that the \n is not entered.
Yes, so we assume we entered more than fit in our buffer, so some long input, and we only read just 4 now, but I want to store everything. Okay. Well, I need to call realloc because we still need to read everything left in the input buffer. I have a visualization for this. So if you compare these two, first I just enter 1, 2, 3 \n with this buffer size of 5. The input buffer is empty. Everything is in our buffer. This is just when everything worked out fine. But now I want to handle the case that I entered more than this. So I entered 1, 2, 3, 4, 5 and then hit enter. So 5 and enter is still in the input buffer, but I want to read this as well. And I can read this by calling fgetS again. But I need to increase my buffer first. So, because we're calling realloc, we need this temp pointer as we have seen. I want to realloc this buffer. And well, to what size do I want to do it? I somehow want to increase it maybe by 5 each time. But maybe to make this a bit nicer, I could create this buffer size variable, which I set the buffer size at the beginning. And then before the fgetS, I can just increase it by buffer size. No, before the realloc. Also here, I can use this buffer size now. And now this buffer size stores the new size I want. So at the beginning here, the buffer size was 5. I read 5 characters, and now I want to increase it again by 5. So this buffer size is now 10. Size of chart just for completeness. And the null check. If
now I'm watching you that you do everything correctly.
Okay, if this is null, then realloc didn't free this buffer, but we want to return, so we need to free it. And now we can just return with some error code. And if everything worked, we can set the buffer to the temp variable. So we now have an increased buffer. So now I want to call fgetS. Yes? Okay.
No question, apparently.
Now I want to call fgetS, but with what parameters? I don't want to write from the beginning again. If I did something like this, yeah, so with the new buffer size and std_in, this would be wrong because our buffer stores this here. We increase this buffer, but if we now just pass this buffer to fgetS again, it will write this 5 and this \n here in the first 2 slots. So it will override what we have written before. So this is what I drew here. after this realloc, we have this bigger initial, here it's initial buffer, but in our code it's just buffer. And if we would just pass this buffer to fgetS, we would start writing, fgetS would start writing at the beginning, as it always does when we pass a pointer. So we don't want to pass a pointer to the beginning of the buffer, but to the location where we start, we can actually start writing into our buffer. And this is exactly here where I wrote start at this 0 byte. Because we want this 0 byte to be overwritten by fgetS, because we want our string to continue. If we would start here, then our string would stop here because there's already the 0 byte. Therefore, we want to start here, and we can write until end. So, if we check this now, we want to start writing at the 5th position. We need to add, if we have a pointer to the first element, 1, 2, 3, 4 to the pointer. This would be buffer size -1. And how many characters can we write? 1, 2, 3, 4, 5, 6 characters. Because we overwrite the 0 byte, so we can pass buffer size +1 to fgetS. Let's implement this. I want to write from, so fgetS should start writing from buffer plus buffer size -1. So we increase this buffer pointer by 5 - 1, 4. So it points here, 1, 2, 3, 4. It points here now. And how many characters do we want to read? Well, we want to read buffer size +1 now, because we start already at the 0 byte, so we have 1 byte more where we can write characters. Okay, and in theory now, if I did everything correct, then if we call fgetS with these parameters, it should start writing here, place the 5 and the \n into our buffer, and a new 0 byte, because this is what fgetS always does, and we are finished. We now have this \n in our buffer, we can check for this, and we can stop calling fgetS to read from input. So we have here the to-do that we repeat all of this. Let's try it out. Okay, so maybe let's use this test case here. So 1, 2, 3, 4, 5, and then enter. And as we can see, the 1, 2, 3, 4, 5 and the enter was stored into the buffer. So apparently we did it exactly like this, where everything is in our buffer. But as I just left this as a to-do, if we enter this first case here, where it fits into the initial buffer, we'll be asked a second time to enter input, but we don't want this, therefore we need this check here. Should I implement this now? Do we have time?
I think we have some time.
Okay. So what we do is just some contains function we'll write that this buffer does not contain \n. And just then, if there's no \n, I want to resize the buffer and read it in again. We still need this contains function. So we get a char pointer for the buffer, and we get a character that we want to check if this buffer contains this character. So what can we do? We just loop over the buffer. We can just check if the current buffer, we loop as long as the current position is not 0. We increase the buffer pointer, and if buffer at the current position equals C. We know that it contains, and we can return 1, and here return 0.
It seems there's some imposter in the lecture hall. Okay, we get the...
Did I do something wrong?
You copied the FGDS somehow at the very top, bottom.
Okay. So does this work now? We enter an input that is bigger, it works. We enter an input that is smaller, and it also doesn't prompt us again. We just enter 1, it also works. So we need this check, or else we would get asked into something again, which is not what we want. But as you can see here, we have some initial buffer. We read into this buffer. If we are not at the end, we resize the buffer and then read again from the input. Now, the only thing that's left is repeat this until this condition is false, so until, this condition is false, so the contains is true, so we have the backslash n in the buffer. And this is something I will leave as an exercise to you.
Otherwise, assignment 3 would be taking the code from the practical. So yeah, you need to figure out then in the next iterations where to place the correct pointer, so where to write into the buffer, what size is allowed, how to increase the buffer correctly. And don't do this with 5 ifs. You need to really use a loop here such that it works for infinitely long inputs.
So it's not that hard to plug in the loop around all of this, but it's also not completely trivial. You need to be a bit careful with how you choose these indices here, that you start writing at the correct location and always know how many bytes you have left to read. So you need to think a bit, think about this illustration. I think then it should be pretty straightforward.
Yeah, it's also allowed to draw a picture on your own there, because I think it really helps if you visualize what is happening. And yeah, as I said before, this should then in the end really doesn't depend on the initial buffer size or on the buffer size that you increase. So it should work if you set the initial buffer size to 5, or it should work if you set it to 10. And it's a really good thing if you test your code for a very small buffer size such that your code is executed. Because if you set it to 1000, then probably your relog will never be executed and you will never test it and you will never know whether it actually works or not.
Yeah, seems like I did everything correct and it works with buffer size 10 too.
This is very nice.
Okay.
You are done. Any questions regarding the dynamic user input?
Yeah, I think if you manage to do it with the get chart, this is just a minor step up from what you did with the get chart in the old assignment.
Yeah, maybe just to get the feeling at the moment, who already programmed or coded a bit from assignment 3? Who started already?
Oh, many.
Oh, that are really many. Maybe this was very boring to you because you already implemented it. Maybe you find out a problem in your code now. Hopefully it helps you.
Yeah. And if you did not do this, then please, implement it.
Okay. Let's move on. Yeah, now we come to the data structures. First we start with the two-dimensional arrays on the heap, and then we will talk about linked lists. 3 weeks ago, I think we talked about the two-dimensional arrays on a stack, and many of you used them in the assignment 2. So this was this Wordle game where you stored a two-dimensional array of the guesses, and then there were six tries where the user can guess. So you had a two-dimensional array of probably size 6 times 6. Now we have here this array of doubles. I think I motivated this that you store temperature values for the morning, afternoon, and evening, and then we have 2 days where we store these temperature values. And yeah, we specify the size of the 2 dimensions. So the 2 would be the 2 days and the 3 would be the 3 temperature values per day. And we also drew a visualization on this where we said, okay, the values are stored in sequence on the stack with the indices 0, 0, 0, 1, 0, 2, and then the second subarray is stored on the stack with 1, 0, 1, 1, and 1, 2. And we also talked about it that this myArray variable, so the actual array variable here, is kind of a weird thing which does not actually exist, but it's a pointer to, yeah, which if we dereference this pointer, then we can access myArray at 0 or at 1, and then if we dereference this again, then we come to the actual values. So we had this construct here that if we write myArray at 0, we come to the first subarray, and if we write myArray at 1, then we come to the second subarray.
Yes.
Yeah.
So it behaves like a pointer to a pointer, but yeah, it's not really one.
Everything is fake on the right-hand side. Yeah, so, yeah. Now we can discuss whether the things become better on the heap or not, but it's definitely a bit different. So how can we create a 2-dimensional array on the heap? First, we need to create the outer dimension of the array. Yeah, so if we move up to this example here, which is very nice here, we see, okay, we need later on for 2 days the subarrays. So we need 2 subarrays, so we need to create pointers for these subarrays. So we call malloc 2 times size of a double pointer, because we learned an array to an array consisting of 3 doubles has the type double pointer. And now we need to create space for 2 of these double pointers with malloc and receive as a return value a double pointer. So double pointer, not a double pointer myArray.
Also note in the size of we have the size of a double pointer, not of a double.
So the crucial thing is really this here, we have double pointer, and here we have a double pointer. Why is that? Just very heuristically, if we move back to the stack array, we also said this 2-dimensional array, we have to follow 2 errors to get to the actual values. So we need two times dereferencation, and this is also the same on the heap. Okay, now we have created the outer array, and now we can loop over the size of this array. And inside of this array, so the values that we can store are double pointers. So we can here allocate arrays of size 3, so 3 times size of double with malloc and write in myArray at position I. Okay, it seems really odd maybe it was not the best way to explain it, but pictures are usually better. So here is the picture of the array on the heap. We have the myArray variable. The myArray variable is a double pointer. So it points to an array on the heap. This is just this little guy here, consisting of 2 values. And what is stored there are 2 double pointers stored. So we can store 2 addresses here. And the address of the 0th element that we store here, this is the address, if we follow the arrow, to the first actual subarray of values. So these 3 values here are the first subarray in the 2-dimensional array. And then we have here in the outer array a second pointer, and this pointer, so this address here of this pointer, this points to the second subarray in the array. So we really have this construction of 2 pointers. We have this double pointer. We need to go to the first array which is stored on the heap, take the correct address of the subarray that we want to access, and if this would be the 0th one, then we need to follow this arrow to go to the first subarray, which consists of these 3 values.
Maybe also note that these arrays don't have to lie next to each other on the heap. So we have this array with the 2 addresses, then there could be some space. And for example, we have the array, this one here with these 3 values, and there could be some space, and then we have the array of this one here of 3 values. So the only important thing is that here we have the correct addresses in the first array, and that here we have the correct address to this array of addresses.
Yeah, it seems really a bit difficult here. Maybe make it more precise when we access a concrete element here. So my claim is that my array evaluated at position 1 and position 2. So if we go back to the picture, 1, 2 would be this element here. I wrote the indices here, so it's 6.7. This is the same as taking my array plus 1, dereference it, add 2, and then dereference it again. Okay, let's look what this means. So I'll start with my array plus 1. So I have it here a bit larger. My array stores an address. If we add to this address plus 1, then we do not have the pointer going to the first position of the array of addresses, but actually we have a pointer to the second element of this array. This is my array plus 1. This is a pointer to the address, to this address here. If we dereference this now, then we take this address, follow the arrow, and come to this element here. So my array plus 1 dereference, this points to this element or to this element consisting of these 3, so of this array consisting of these 3 values, depending of if you think a pointer points to a single element or an array.
Yeah, so my array plus 1 dereferenced is again a pointer which points to the top array. And if we say it points to the top array, we mean it points to the first element of the top array.
Okay, what can we do with that? We have this, the violet thing is a pointer. My array plus 1 dereference is a pointer to this thing here. If we add plus 2 to it, then we just take the array here and go 2 positions upwards. So this is my array plus 1 dereference plus 2. This is a pointer to the element which is here marked in violet. And if I dereference this again, then I actually get the value. So to sum this up one more time, my array points to the array of addresses. If I add something here, then this means I go to the correct address of the subarray. If I dereference this, I go to the correct subarray. If I add something here, I move onwards in the subarray. And finally, if I dereference this value again, I reach the value that I want to achieve here. So this weird expression here, my array plus 1 dereference plus 2 dereference, is the same as if I would write my array at 1, 2.
Yeah, so always use the second form. So write my array 1, 2, because this is way more clear what you want to do.
So the big change to the array on the stack is that if we look on the stack back, we had this fake construction here where we could just write 0 and then come here and write the 1 and come here. And on the heap, we really need to implement this on our own. So we need to go to the array of addresses, and from this array of addresses, we can then move onwards to the actual subarrays.
Yeah. So this heap to the arrays, these addresses are actually stored somewhere. And unlike the stack array, don't just behave like pointers, but really are pointers that are stored on the heap.
I know that this is, I really must admit when I explained this now, it seems more difficult than it is in practice. It's probably something which you need to try on your own for one time. But basically, this is the code that you need to use. And remember, you need the double pointer here. And because you need to store an array of addresses first, and in this array of addresses, you can go to the correct subarrays, which you do here.
Yeah, maybe one a bit more tricky question. If this inner malloc here fails at some point, which addresses or which blocks of memory do we need to free?
So if this malloc fails here, then we have a loop outside of here. So if this malloc here allocates the subarrays, where we really store the double values then. And if we successfully allocate 10 of them and the 11th failed, then we of course need to free all the 10 subarrays here that were successfully allocated, and we also need to free then the array of pointers. We need to free everything all the time. So this implementing the null checks in the two-dimensional array is a bit tricky. Yeah? But again, once you have set this up correctly, you have more flexibility than on the stack, because nobody says that you need to have all the subarrays of the same size. You could have a subarray of size 3, one of size 10, one of size 20. So this is not necessarily the same size. And you can, of course, reallocate the two-dimensional array. You can reallocate the subarrays, so where you have the double values, but you can also add new subarrays if you reallocate the double pointer outside. So very flexible, but it's, of course, it's a bit complicated, or it's more complicated than on the stack. Do you have something to add, or I explained everything?
Yeah, I think it's fine.
You have any questions? Yeah?
When we free a two-dimensional array,
Yeah?
you have an order to free things, which one to free first, which one to free second?
Mm-hmm. So the question is whether, so if you have a two-dimensional array and want to free the two-dimensional, if there is a specific order in which we need to free the resources. Yes, this is the case, because, maybe go to the picture. This blue thing here is a malloc, and all the blue things here are mallocs. And if we first free this address here, then this array here is freed. So we cannot access these addresses anymore, because this array, which I mark now, this is not a valid memory anymore.
So we just lost the pointer to all the mallocs we did inside the loop. But we need to free them, or else they leak, so we can't do that.
So we need to first use this pointer to go to this array, free this address, free this address. So this order doesn't matter, or if we start with the address of 1 and address of 0, this doesn't matter. We need to free all of them, and once we've freed all of them, then we do not need this blue array here, and can also free the outer dimension. Yeah, then we can also free this address. So when we allocate the resources, we start from outside and move to the inside. And if we free it, we need to do it exactly in the reversed order. So we need to free these arrays first, and then we do not need these addresses anymore and can free this array as well. So there is really a specific order required.
Yeah, maybe it's always a nice idea to order in the reverse, to free in the reverse order you malloced. So things like this can't happen where you lose some pointers.
Yeah. Any further questions? Okay. One more data structures, linked lists. Probably conceptually a bit easier now than the two-dimensional array, and I think you have heard more about it already in the last lecture. And the idea was basically that we first need to create a struct for our list elements. Structs, we learned about them at the very beginning of the course, which a struct combines multiple data types into one new data type. And now we need to store the actual data that the linked list should hold, for example, integers, for example, students, for example, songs in a playlist. And we additionally always need a pointer which points to the next element in the linked list. So these are the ingredients for a linked list. And yeah, we want to do it with coding.
2D linked list.
No 2D linked list. Just a very simple linked list which just holds integers. And yeah, a bit more advanced. We not just want to create a linked list where each list element contains an integer, but the list should also be sorted. And it should be always sorted. So we want to add elements to this list. And when we have a sorted linked list, add an element, then the element should be added at the correct position in the linked list, such that the list remains sorted.
Yeah. Last time in the lecture, you already saw the code, how to implement such a linked list and then how to insert an element, always at the same position. We just want to do it a bit more complex and insert this element always at the specific position so that it remains sorted.
Yeah, exactly.
Yeah, and I think removing an element you will see today in the lecture. Or not?
Maybe this is a homework. Homework.
Okay,
Removing
homework,
an element is homework. Okay. Okay, then let's start coding. And must admit I prepared a bit because I don't want to do everything. Because this is more or less trivial. So we have this struct which contains the list elements. It should contain the data, which is an integer, and it contains a pointer to the next element. I will write functions to print the list and insert a new element sorted in the linked list. And I also prepared the main function already. So we start with an empty linked list, which does not contain any elements. We print it, and then I already prepared some numbers. And for each of the numbers, I will call Kellogg, which is the same as malloc, but it also initializes the memory to 0. Fill in the number and want to insert the element in a sorted manner into the linked list, and afterwards I again want to print the list.
Yeah, and of course don't forget the null check.
Yes, I will leave this as a homework. Yeah, I will leave this as a homework to you. I don't want to do this now. Okay, so probably it would be a good thing that we start with printing the list. So we assume now that we have some list, it's empty at the very beginning, so we cannot test it very nicely, but assume we have some linked list and we want to print it. What do we need to pass to this print list function? It's also rather simple. We just need to pass the head, so a pointer to the first element of the linked list. And this is the pointer to the first element of the linked list. And yeah, we want to print it. We also want to print it here. So we pass just the head to the linked list. And this means we have here list element pointer head. Okay, so how did this printing work? I think there is a visualization somewhere. I hope it's large enough. So assume this is our linked list. It contains the value 0, 1, 4, 6, 7. At the very beginning, the head points to the first element in the list. We can print it, and then we need to go to the next pointer, take the address of it, and move onwards to the next list element. So in this case, the head pointer points to the second list element. We can print the one, we can take the address, move onwards on the address, and go to the next element. And so on and so forth. Yeah, at some point, we are at the very last element. We again print the number of the element, take the address of the next element, and here we have null instead of an address because we're at the very end of the list. And we again initialize head or assign the value null to head. So head points then to null at the very end, and then we know that we have gone through the whole linked list. So this is very important. The linked list is always terminating with a pointer to null at the very end. Okay, so this will be then our condition to check until when we need to loop in the linked list. So we do this here, while the head is not null. And while the head is not null, we know that we are at this, or this position, and certainly not after the linked list. And we can print, I don't know, maybe something like this. Head, this is a pointer to the element, so we need to dereference the pointer. We need to dereference it and take the number. And we have learned something better here. We could also write, instead of the dereferencation and then the accessing with the dot, just head and the error. Okay. And once we've printed the element, we also need to move to the next element in the linked list. So this was what I said here. If we have the head pointed to the first element, then we need to go on the pointer to the next element in the list. So we need to say, okay, head equals head next. Okay, and at some point we will reach null, and then I'll just print a \n here. Okay, this is the print list function. We always print the value and go to the next value. Maybe compile it. Something like this. Okay, and if we go to the main function, we see at the start the linked list is empty, nothing is printed, and at the end the list is empty, nothing is printed because we have not inserted anything yet. Okay, so the printing probably should work. I cannot demonstrate it because we don't have the actual linked list, we just have an empty list at the moment. So we also need to implement the insert sorted function. Okay. So we allocate here a new element for the list. We do some null check, hopefully. The new element gets assigned a number. So now the new element is complete. And now we want to insert it sorted into the linked list. So we need to pass in the linked list. So the pointer to the first element, maybe, head, and the new element. Now in insert sorted, we give the head to the list and a new element. Okay, so we need this also as parameters here. Take list element head and list element the new element that we want to add. And now we have different cases here. The list could be empty. The element could be the smallest element in the list, so it needs to be placed in the first position of the list. The element could be some intermediate value, which we need to place at some position into the linked list, or the element could be the largest element, so we need to go through the whole list and place it at the very end. And yeah, we need to go through these cases. Okay, so the case one would be, which also applies in our case, that the list is indeed empty. So we need to handle an empty linked list. How can we find out that the linked list is empty? The head is a null pointer. So we check if head equals null. We need to do something. Here, and then we return, because then afterwards this base case is complete. And we could say, okay, head equals the new element. Now, because the head is the pointer to the first element in the linked list, and the new element should, and the head should point to the new element. So we assign it here. The new element next pointer is already set to 0 because I used calloc before, so that I really have null. So it should be fine.
But does this really work?
Opinions about that? I know this is maybe a bit tough.
Who thinks this works?
Huh?
Who thinks this doesn't work?
Few more think that it doesn't work.
Maybe because I asked.
Yeah. No, run it. And we have the problem that start and end the linked list is empty. No values are displayed, but at least the first element should work correctly because we handle this case. Why is this the case now? List element head. This is a pointer to the first element of the linked list. So it has the value null in our case because there are no elements. If we set head to new element, then this head changes to new element. Now, if I would write here, instead of this, I would write integer, then probably it would be clear to you that only the head inside of this function changes and not the head in the main function changes because called by value. So if we would have just an integer here, assign some value to an integer in the function, then outside of this function, the integer is not changed. So if we think about this as an integer and we have here the insert sorted, then this head, which we pass to the function, does not change.
Yeah, but this was tricky to see because it was a pointer, but still we didn't change the content where the pointer points to. We changed the pointer itself, which was a copy. The pointer was copied.
So basically this list element head points to null, and also the head, I will just write list element again, points to null. Both are variables, both store addresses, but these are copies of each other. The two addresses, they are two separate variables that can store addresses. As with the call by value, we have two separate variables that store integers. We now have two separate variables that store pointers or store addresses. So the solution in the integer case was just to add, take an integer pointer instead of an integer. And also here the same applies. Instead of taking a list element pointer, we need to modify the pointer itself. So we need to take a pointer of the pointer. And also here in the insert sorted, we need to pass in the address of the list start
Pointer.
Of the list start pointer. So it's such that we can modify this pointer here. Okay, get rid of this. When we want to do something with this pointer now, we need to dereference it always. We dereference it. Now this is equivalent that we take the value of this variable here. Check if it's null, and then we also dereference the head and assign the new element to it. This is equivalent to assigning new element directly here to this variable, because we have the pointer here. Okay, check it again. This now works. So the first element, I think we have 4 here. Yeah, So at the start, the linked list is empty, and then afterwards the 4 is placed here. I also have the visualization, but I think it's a bit trivial here because we had that head points to null, new element points to the element, and we need that head points to the element. Yeah, okay, this is what we did with that code. So inserting it, if the list is empty, works. Now, come to the next case. The next element that we want to insert is the 1. And the 1 should be inserted before the 4, such that the list remains sorted. So we can implement this. Okay. So we check if we take the list start. We always need to dereference it from now on. And check whether the number of the first element of the list is larger than new element number.
Yeah, so notice that with the first number after the head, we have 2 dereferences now because we have a pointer to the pointer that points to the list start. So we need the dereferences to get a pointer to the list start, and then this arrow dereferences it for us, and we can get the number.
Yeah, more or less 2D array, like 2 differentiations here. Okay, now assume that the first list element is larger than the element that we want to add. What do we need to do? Maybe the picture is now better at the beginning. So we have this situation, the head points to the element with 4, the new element points to the element with 1. And afterwards, we would like to have the situation that the head points to the 1 and the 1 points to the 4, because then this head to 1 to 4 is our linked list. If we take head next equals new element, this is not possible because then we overwrite. No, this is completely wrong. If we take head, so the start of our linked list, this should point to the new element. This is what we want to achieve. Head should point to the new element. If we do this right now, then we lose our remaining linked list because head points to the element 4. And if I just assign the new element to head, then we would have here a pointer to new element, but we would lose a pointer to 4. So it's important that we first take the new element, assign the linked list to the end of the new element, and then take the start of the linked list and let it be the new element. So it's crucial that we follow this sequence of the instruction. If we do it the other way around, it wouldn't work because we would lose our linked list completely. Okay, let's check whether this works. Okay, it even worked better because we insert multiple values, 4, 1, 2, 7, and then 0. And this worked because the 1 was inserted before the 4 and the 0 was inserted before the 1. So these 3 numbers already worked. Inserting at the beginning works. These were more or less the base cases, and now we also need to implement inserting in the middle of the linked list or at the end. In these cases, we probably do not want to change the head anymore because the head should remain the start of the linked list. We do not change the first element of the linked list. So it's beneficial if we take a list element pointer iterator equals head. So if we change the iterator, we do not change the head of the linked list. So this stays the same.
Yeah,
and
so we copy the pointer.
We copy the pointer, yeah. And now we iterate over the linked list. And I will do this now with an infinite loop and hopefully terminate it at the right moment. Okay. When do we have a very trivial stopping criterion? If we reach the end of the linked list. So if iterator next equals null. Now what does this mean now? If we are here at this point in the code, we know that there exists certainly a first element, and we know that we do not insert our element before the first element. So we always keep track of the first element and the next element of the linked list, because we know we don't need to insert the element before the first one, so we need to certainly insert it we need to insert it at the second position, third position, fourth position, but not before the first element. So we can always keep track of the first element and the element afterwards. So we keep track of two elements. One element where we know we don't insert before, and the next element. Why is this necessary? If we want to insert the element in between those two ones, we need to keep track of two elements at the same time. So our iterator points to an element, and iterator next points to another element. It's a consecutive element in the linked list. And we need to check now if we need to insert our number between the iterator and iterator next. And now we start with the more trivial case. So if the iterator next equals null, this means that our iterator points to the last element in the linked list, and iterator next is then the pointer to the next element which does not exist, so it points to null. So we need to insert an element certainly at this point here. And what do we do here? We basically say, okay, iterator next is the new element, and maybe new element next equals null. So this means iterator next is null. We reach the end of the linked list. Iterator points to the last element in the linked list. We add the new element after the last element and say the new element points to nothing because it's now the last element in the linked list. And in each iteration, we of course need to increment the iterator. Maybe try it, and then we have also visualization here. So this already works for the number 7 because it will be placed at the very end. I hope I did it now correctly in the order. Yeah. So we take the iterator. The iterator starts pointing at the head. Okay. We want to move to the very end of the list, so the iterator also needs to point. So we increment the iterator such that it points to the previously last element. So the 4 is the last element, and the 7 is what we want to add. So we have this iterator here, and iterator next is this value here, which initially points to null. So this arrow is not here at the beginning. And then when we want to append the last element to the list, we need to set this pointer to point to the new element, and new element points to null. And this is what we implemented here.
Yeah, if you compare this looping technique to the one I did before in the string, where I incremented the pointer by 1, so it points to the next element in the string, and then checked if this is null. This is very similar, but instead of just incrementing the pointer by 1, we need to set the pointer to the point of the next element, and the null check is also very similar. We just check if the next element is null.
Such that we have reached the end of the list. Okay, so we know how to insert at the end. So basically what we've implemented now is empty linked list is correctly done, first element is correctly done, and last element is correctly done. What if we need to add an element in the middle? We consider this here as well. So if iterator next equals null, then we reach the end and we need to insert it. or if the iterator next is larger than, no, iterator next number is larger than new element number.
Yeah, so when the next element, the number we stored there is bigger than the one we want to insert, then we know we are at the right place to insert our element. Because the last one was smaller, because we didn't insert it there and return, and the next one is bigger, so here we must insert.
Well, I have a visualization for that, what you said. So if we want to insert 6, we know 4 is smaller, 7 is larger, we need to insert here in the middle. Okay. Iterator next equals new element. If we do this directly, then we lose the remaining linked list. So we cannot do this in this way. So we can change the order of these two for this case without problems. And we say the new element next should be iterator next. So this basically means we set for the new element which we want to insert the address here correctly. And afterwards we need to implement this error here. So from the iterator we need to go to the new element, and I think we have this here. Iterator next should be the new element. Okay, and with this we inserted the element in the middle of the linked list, and we can give it one more try. And now you can see that the list is perfectly sorted here. Because whenever we insert an element into the linked list, we insert it in the right place. So afterwards the linked list is again sorted. And then if we insert one more element, we have it sorted correctly. We insert an element in the correct position so the linked list remains sorted. But it will always be sorted if we do it this way. Okay, yeah, we managed to finish here. Yeah, we have done it for today. Yeah, so we started with the dynamic memory, the user input, which is very useful for F3, and then the data structures with linked list and to-D arrays on the heap.
Yeah, and with those data structures examples, you might notice how important it is to really understand how pointers work. Because even with those more or less trivial examples where we just wanted to insert the element in a specific way, so sorted, we already needed lots of shuffling around pointers and knowing how they are laid out in memory. And yeah, so if you're trying to do more complex stuff, the pointer stuff, of course, will also get more complex. So you should really understand the basics.
And also a slight hint here, the linked list is very often part of the exam. So such examples, inserting an element to the linked list, removing one from the linked list, you should know this by heart for the exam.
Yeah, but I think the lecture team will talk more about the exam at some point.
I think today even, yeah.
Yeah, okay, yeah.
Yeah, then here you have 10 minutes break, and at 4:45 the lecture will start with the last topics. Okay, thank you.